Sure.
Okay. Okay, I'm gonna share my screen. Okay, so this is Ilastik. So this is like a very common tool, like recently developed for segmentation and tracking of cells. There are two main things. Like one can be good, other can be bad. This is uh, like it's a neural network, but you have to train by yourself the data. So in the repository, there's some example of data sets. So I'm going to show you more or less. So here in images, you have like 3 channels. GFP corresponds to the filter of green fluorescent protein. So here is gray, but it corresponds to the intensity of the green pixels in the image. RFP corresponds to image series M cherry. So you can see here how are they. Okay, and yeah, this is the red filter. I think it's M cherry fluorescent protein. And gray, I think, is the merging of all of them. So here I instead of I painted in blue in the M cherry protein and in green the GFP. So you have here the merging of all channels. So I'm gonna use maybe this for segmentation. So the idea of the segmentation is try to distinguish which part of the image is cell and which part is background. So these images are in format .tiff, as you can see here. That essentially corresponds to the like more basic kind of image. It doesn't have any kind of like vectorial or like other kind of decodification. These images correspond to a pure matrix. Each pixel has a value that corresponds to the intensity. If you have a RGB, like red, green, or blue image, the image is gonna be, let me share here the screen. So in adaptive image, for those that are not familiar with this extension, the image is an array, like a matrix, and each component corresponds to a pixel. So if you are RGB, you have a pixel of 3 elements, corresponds to red, green, and blue. So this is depending on the codification of each byte here. This can be usually is I think it's 8 bits. So this corresponds to a number between 1 and between 0 that corresponds to no intensity to 1026 if I'm not wrong. So the higher the number, the higher the intensity of the intensity of the light for each particular color. So we're going to use the Python libraries to manipulate the image in this format. Okay, so the other format like PNG or JPG are not recommendable. Okay. Okay, so for Elastic, we're going to need essentially 2 tasks. The first one is the pixel classification that tells you if you have cell or background. So it's going to give you something called mask that you can also decodify in .tiff files. So you can to any pixel of your image assign a number, let's say 0 to the background and 1 to the cell. So we can like start with pixel classification. And after that, we're gonna do manual tracking or tracking. That corresponds to, given the contours of the cell, tracking the same number, or give some numbers to particular cells and track them. Okay, so we start here with create new project. So I'm gonna save this in my file, in my folder. So I have my images here in images. So it's gonna be pixel. mm, Classification, if I'm not wrong. And it will start. Okay. So I can add new images, and I go to my folder. Uh, so I'm gonna use here, sorry, image, let's say gray. So you can see here. So this image have the same name, post 0t, and have a number in the right. Like we call it the suffix. Like it tells you like the frame of the uh, movie. So 0 corresponds to time 0, 1 corresponds to time 1, like in frames. They are sorted on time. Okay, so let's say we open this one, you and the program that you can import it, but I'm gonna import all of them. In this case, I uploaded 50. But I think the actual video has around 300, but I didn't do it because segmenting such amount of uh, frames is too much. Okay, so here we select the next step. Once we upload the first data set, we can do the second step, and then we can do the 3 or 4 and 5 step. So here, this neural network use different kinds of like properties of the image, like the color, the intensity, edge, texture, and also have kind of a convolution with some Gaussian filter. Like, I'm not sure if you need this kind of details, but the idea is like this gives you like the size, more or less, of the region you're gonna consider. So the smaller the point, the smaller the kind of regions you're gonna use in your neural network. So these small points split the image in smaller like points, and this big considers bigger regions. It depends on also the speed of your computer, the number of features you're gonna use for training the neural network. Yes, so I'm not very expert on which kind of uh, like features are optimal, but the program also helps you to get the best features, but this is gonna be later. Okay, so now the program is mm, like setting the neural network, and we can go to training now. Okay, so this is like you can see here like each feature consistent. So you have like some convolution with Gaussian distributions, like with 2 dimensions, and also like other mathematical aspects. Maybe there's no need to not too much. Okay. So here, like, is the manual task is like to paint the two labels we want to like segment. So the first one is gonna be um, the background, and the second one can be cell. So here with this like the window, you can check. You can paint using this like the brush button, and size you can increase or decrease the size of your tool. Let's say yellow is gonna be the background. So everywhere I see background, I can paint it in yellow, and I can use zoom using control and the wheel in the mouse like this. So here I made a mistake, so I use the eraser and so on. So with blue, I select the cells so I can go zoom in and I try to paint them more carefully. Like this, like this, even like small cells like that you barely distinguish. So the more time you spend on like doing this manual verification, the better is gonna be the training of the neural network in the future. So you can go use another figure. For instance, I have here position 0, and I can go to other position, let's say position 5, and continue my training with another image. So yellow for background, blue for cell. Okay, so there's so I use here the two like filters, the Cherry and the GFP, because I think they consider the program consider the sum of all both like pixel values in the both channels. Okay, so let's say I finish. So the idea is like to do the as much as you can, and then I can click here on live update. And here the program is training the neural network with the input, and the program is gonna give you like a preliminary segmentation. So you can here increase the intensity of the prediction, and you have here like the possible segmentation. So you can check, you can compare with the image, and if you are okay, you say I'm fine, or otherwise you can like check not only this one but also other photos. Let's say this one, like this, and this is like the prediction for this image. And if you are happy with that, you can like leave it like that, or otherwise you can like continue the labeling by hand. So I can make this. So for instance, this guy was a cell I didn't detect. So I paint in blue the cell and in yellow So I'm gonna click out, click again live update. Every time if this live update is like playing, it is gonna train every time, but sometimes the input is so high or so many inputs that the what? The the computer is gonna take a lot of time to train. And that's it. You can go to other photos and so on. Okay, let's say I'm happy with the prediction. So I can go to prediction export, and here you have all your data set, like your 50 photos. So I can choose export image setting. So usually I like to work in .tiff. So I can export the data as a TIFF sequence. Sorry, not TIFF sequence, it's only TIFF. And I select my folder. I don't know. I can make a new folder. This can be, I don't know, prediction. And you save them here. Okay, so as you can see here, the shape is gonna give you the number of bits of pixels, sorry, on first Y for vertical corresponds to 970 pixels, 1700 on or horizontal, and 2 pixels in Z axis that corresponds to 0, the background, if I'm right, or 1 cell. So these kind of images we're gonna call masks because corresponds to uh, like a binary image that tells you what is cell and what is not. So, okay. Mm, and I can export all. Mm, I don't know what happened. Okay, okay. I think here I choose to export probability. Let's see if it's a simple segmentation. Let's see what happened here. The same. But if I do I have no idea what happened. Okay. Here, maybe the name is something with the names. Okay, let me check more carefully. Maybe next time I can explain you better what happened here. I think maybe it's because of this space or something like that. Yeah, but if everything is fine, what you're gonna get is this kind of files. Can open here in Fiji that corresponds to a image of masks. So here I change the name for prediction 00. Maybe it's the name, but I don't remember how to modify the name. Okay, so this guy has the same name. So this is like the directory. So if you see here, like the exporting is gonna be to the same file. So let's see, let's use batch processing to get the images. Maybe this is better. You solve the image here. There's something with the names, but I check it more carefully later. Okay, so the result is gonna be something like this, that gives you 0 in the background, like pixels with value 0. You can check here the value and the coordinates. So each cell is gonna have a different name. So this cell is, oh no, this is like the prediction for the math. Uh, let's see if I export this as stage. Okay. Okay, once we export this, we have we're gonna get the mask. So with the mask, I don't have them here, I think. Uh, you open a new project with, let's say, so this like after this pixel classification, you open a new project with manual tracking or tracking, sorry. So for this, you're gonna need the images, the raw data, and the binary image that corresponds to the segmentation that you export. So here I had the manual tracking workflow corresponds to this. Sorry. And we have here, I have here the exporting, sorry, the pixel, the prediction. Yes. So it gives me gives me the binary segmentation for all cells. So green is the background, red is the output. So you import it. So here it seems like this guy is this prediction. Okay, so I save it as a H5 file. I didn't remember it was a long time ago. And we go next to threshold and size filter. Here we can like modify a little bit the segmentation. And with manual tracking, I can select different cells. So I started with one, so start new track. Let's say we want to track I don't know, this cell. So the yellow corresponds to a cell that doesn't have any label yet. So start new track, I use this. Okay, so if I go in the previous one, this cell is gray and its name is 191. So for next frame, I select the same one, but now it's death in this frame. So let's say I can start a new one, start new track. Let's say this, and I track the cell for all the time the program detects it. I'm just clicking the segment, and the program is gonna give it the name of 192. So I did it for all the cells. So here, this guy seems to abandon the frame. So it's not always good. And I export the data again. This has TIFF sequences. The other one was H5. So sorry for that confusion. And I export it. And I can now open the Python script that I sent you. Let me check. Where is it? Okay. Okay, so this is like the program I sent to you. So I'm gonna use here the libraries for image processing CV2 and Schemage. Also like the classical libraries of NumPy, Pandas, TQDM for check the time for that my script is taking, and matplotlib. Okay, so here my output is this. So in my image, like the raw images are in gray. And they end with a .tiff that corresponds to the raw images. So with this like code here. I'm gonna save all the TIFF images in this folder, in this array called files. And in manual tracking, I have also the predictions. So I save also all the files there. So if you check files here, you have all the positions. If you check here, the directory of masks, you have, oh, sorry, this files masks. You have all the masks. Okay, so here I define some colors. Like this idea is like given the name of the cell, I select, uh, I have 9 colors that I pick like randomly using, this is the HTML code for each color. So you can check it here, which color is each one. So this one, let's say, is this blue. And I'm gonna give the name of the cell, and I select the module of the name in base 9, and depending on the module, we're gonna get different color. Okay, I'm gonna make this path, videos and figures to save everything. And what does this script does? Okay, so for all the files, I'm gonna read the file that corresponds to the image, the masks, and I'm gonna plot the image using, first I'm gonna read the both files. So the mask I'm gonna use as a gray that corresponds to, like, it makes the array of, let's see. So an array of RGB, if I read it as a blue, I think gets the average value of these three, and this array of a matrix with 3 elements, each of them is gonna become only 1 element. So it's not RGB anymore, but it's only one number. Sorry, it's one number. I don't know. One. Okay. So red filter corresponds to uh, the channel 0, and green 1 and 2. I mean, for the image that is not gray but RGB, the first element is the red, the second element is the green, and the third element is the blue. Okay, so I'm gonna like split the channels in these 3 components. So the mask, I read the mask, plot the image, and for all the masks, and a small mask is gonna be the pixel, such as the pixel has value. Let me show you here more carefully. So for with this Matplotlib AGG, you don't plot here the output like in the script. With Matplotlib inline, you do it. Okay, so let's see how is binary. So for doing this, I use PLT IM show binary, and this gives you like all the like the segmentation with different numbers, meaning different cells. So here you have cells that are more yellow, that corresponds to cells with higher name, and cells darker that corresponds to cells with lower name. Yes, so background is 0, you can see here. And there's going to be a cell with number 1 that maybe is this one closer to like darker. Cell 1, cell 2, cell 3, cell 4, cell 5, 6, 7, 8, 9, 10, 30, 40. You can check it using unique. NumPy, unique binary. So these are all the cells that have given name. 1, 2, 3, 4, 5, 6, 7. So in total, it seems that I have 188 for this data set. Okay, so if I check, for instance, binary equal 63, I have an array of false and true, and all the points that have cell 63 are going to be 0 elsewhere and 1 or true for 63. So we can even plot this guy. Corresponds to this cell. That is 0 elsewhere and 1 if binary is 3. So here I'm checking the mask such as the binary is the name that I have. So I'm doing this now. Because this 63 is a number. If you can check it here. And this function find contours of your masks, like to your small mask. And you can plot the contour. Okay, so let's say we can do this for this single mask. So let's say we have this. This is the cell 63. Okay, so we call this masquita, no? And if you see here, I'm using for the color of the contour, this function I explained you before. So depending on the label of the cell, you're gonna have different colors. So this is something for control the colors of the cells. Okay, so here is only the contour of the image. I can also like plot the mask and the contour as well. So you can see here the contour. I can like for making more visible, I can paint it in red. And you can see here that this is the idea. So what do I do this? I do this for plotting for safe for all images, the contours of the cells. Okay. So as a result, we're gonna have all the image with contours, and I'm gonna get something like this if I make a video with all the contours. Yeah, so here, like the main thing is like even those cells keep the same name. Let's say this is always 63, the color in the function color HTML is gonna be the same. So here you can like check the results better, the result of your tracking, and to track better every particular cell if you want to verify like by eye what is happening to the cells. Okay. So here for plotting the video, I stopped this guy. But overall, this takes time, so I didn't continue all the frames, but you can like check with the other. So this is the result of the first image. So I am saving here the figures. So I given the name of II, frame II corresponds to this counter. So what we're gonna get is in the plot the folder figures. Not here. You're gonna have frame 0 because it's the first one. And if you do this for all the here, I only selected the first element of this array, but I can do for all of them. But this takes time. Approximately 8 seconds per figures. It's gonna be 200 figures or 50 figures, so 5 minutes more or less, if I'm right. And with this script, it takes all the image in figures and save it in the folder videos, and the name is going to be tracking MP4, and it's going to be your video. Okay, like in videos, you have all like the result that is tracking MP4 that is corresponds to this video. So maybe you can check more carefully. Maybe next time I can help you with the questions. And this last one corresponds to the script for obtaining this particular tracking for all the cells, so that you can like verify more or less if this cell size makes sense or the tracking is correct, how bad, how good is it. I'm not expert on this kind of dimensions, so I'm not sure if this tracking was fine or was wrong. So you guys know more. So the idea is the following. In upper left, you have the context of the cell, so you can also verify if there's like some mixing with another cell, or like check the neighborhood of the cell. In the middle, you have like the intensity of GFP. But the bad thing is like the intensity of the GFP is Ruiz scales, which has the brightest. I'm not sure, but it's Ruiz scale with the total GFP of the contour. So it can give you only like a simple idea of the GFP. Let's see here, like you see here in the beginning, like in this point, you have a cell more brilliant in the left. So it looks like the cell got darker, but actually it's similar intensity than here. Okay, so maybe because this cell here is more brilliant than the one we are studying. So maybe this can make confusing for you, but but it is, I should check how to fix this problem. So the same with the red. Okay. So how to do this? So I define, so I get the contour. The contour is this array or these coordinates. Okay, so as an example, let's see, let's say contour. Okay, so the contour corresponds to an array with coordinates x and y that gives you the position of each point in the contour. So when you plot it, as you can see here, you select as x coordinates the second coordinates in each of the pairs, and as y coordinates the first pair, the first component of each pair. So for y, you're gonna get this, and for the other, you're gonna get this, and you can plot a line with both arrays of coordinates. So you can also use the function measure point contours. What do I use? Get shape. So get shape is defined here. So the coordinate in x is gonna be the minimum. The coordinate in y is gonna be the maximum in these coordinates. So the minimum of these guys, I'm gonna consider it as x. The minimum of this, no, the opposite. The minimum of these are the coordinate in y, and the width is the maximum of this minus the minimum of them. Okay, so like more detailed. You have the contour. So each point of the contour have coordinates x and y. Let's see, let's say, sorry. So the minimum of x, let's say this one, is gonna be my coordinate x. And the minimum of this guy, let's say this, gonna be my coordinate y. This is not x and y. And the width is gonna be the maximum, that is this, or the height, sorry, minus y. And this is the maximum x, and the width is the minimum or the maximum minus the minimum. Something like this. So I have the coordinates of the contour and the width and height. And I crop the image like from like the minimum of my contour is gonna be, so it's like this. So given my coordinates, x and y, so I'm gonna crop the file or the photo adding 30 bits, 30 pixels here and 30 pixels around. Okay, and so on and so on. That was my first idea. But in some cases, the file is cropped here, like you cannot get 30 pixels because the cells is very next to the edge of the frame. So you have to select either 30 of the minimum of of this coordinate because it's the edge is gonna be 0, like the pixel 0. So you select the minimum between 30 or or 0, like y minus 30 or 0. And the same for the maximum, the minimum between y plus the height plus 30 or the maximum height of the pixel. And the same x min or x man. And I'm gonna crop the image using this coordinate. So I select the array from y min to y max and x min to x max. And the same for large, but in this case, I'm gonna use 200. This corresponds to this large image. So more or less from this edge to from this point to the edge is approximately 200 pixels. And from this edge, or like the contour to the edge, it's approximately 30 pixels in this case. Yeah, we are almost finished. Thank you for the patience. So shall I do this? I crop the image, measure the contours, plot the image for each coordinate, and then plot the small contours in the frame AX00. That because what I did was this is an array of matplotlib, so this has the coordinate AX00 for plotting. Now this is AX01. This one is AX02. This one, sorry for my handwriting. And this guy is AX10 and so on. Mm. Okay. So in X00, I plot the image, I crop it, plot the contours, and for instance, for the signal of GFP, I select the mean of the cells inside the contour. Okay, so this is the way that I can select of all the pixels that are inside the masks. Okay, so this mask is cropped as well and is true or false. So 0 for false and 1 for true. And all the pixels in the filtered image of green, such as in the binary mask is 1, I select those pixels and I take the mean of those pixels. And the same for the signal red. And I save it in an array called GFPR and RFPR. Okay, I plot the figures. And I plot also, what is this? This yeah, the plots of green and GFP, like these guys, no? So this guy corresponds to, or the value of GFP corresponds to the average intensity of GFP of this image inside the contour. right? So each pixel of them, you can also check each pixel here is going to have a different value of GFP. And if you select the mean of all these points, you're going to get this value. And for size, I sum up the number of pixels in the contour. So in general, for instance, this contour has around 200 pixels. So this doesn't have like a size of micrometers or not, but only pixels. If you know better this size per pixel with your microscope, you can like convert this into micrometers square or the dimensions you prefer. Okay, so I think that's the main idea. You can like check more carefully. I save the figures again in this folder called figures. And then once I finish this loop for all the cells, so you see here, I started from 2 because the cells 1 is the background. So I'm gonna use only cells like that are not the background. And I do that. That's it, no? And I finally export this, like from the figures, I get the video call cell and the name of the cell, MP4. So you can see here that this is the cell 48, this is cell 78, cell 128, and so on. So I think these guys are sorted by size. Okay, so here what I did also was like if I lose or lost the tracking, let's say here, I want to verify that it was a problem of tracking. For instance, in this case, you can see here that the cell seems to be like the tracking was wrong because here you have the cell, but then something happened and the segmenter didn't detect it. So I continue tracking. I continue the tracking for a couple of frames more to check if was like a problem of the segmenter or not, like to do the manual verification of the tracking. Yeah. So after losing the tracking, I check if the cell is still there, and I increase the previous contour to 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 watch it better. So this part of the code is here. If I detected my contour, I do what I told you. Else, I just crop the image with the same coordinates that I did before. And I plot the same contour, but deleted. What bigger, but I'm not sure. Yeah, here. So it's the opposite. So here I deleted the contour with a disk of 10. So this given the contour with this deletion, you have this effect of increasing the contour in the end. So usually what do we do with this cell? Probably go back to the segmentation and verify the segmentation with the elastic and track it in the again in the or simply discard if we have enough cells. Discard this cell. So I was saving the fluorescence data in full data. You can see here that in the array full data, I was saving cell I corresponds to the frame, cell size, GFP, and RFP that corresponds to the mean of the intensity. And I save it in full data, and I save it in as CSV file in Lysis Dynamics. So we can check. I don't have it here, but I have it here. So in each of them is gonna be like in different columns, cell, frame, area, the value of GFP and the value of red fluorescent protein. So the name of the cell, and each frame. Okay, so this cell have has track from 0 to 15, and this is the area of that cell for each frame, and this is the GFP intensity of that cell for all the 15 frames, and the same for RFP. Okay, so with this kind of data set, you can like select, let's say, all the data points which has the cell is three. All the parts of the data frames which has the cell is 4, or all the data frames which has the frame is 0. So that's why I do here in the next part of the script. So for instance, here for all the cells in the F cell uniques, this function unique gives you all the cells in the data frame. So I can like do it quick. Yeah. You can see here, this PD is pandas, no? If for those ones that are not familiar, the pandas library. So if I do this, let's call this DF. And I select cells such as the DF such as the cell is 2. So I have all the data such as the cell is 2. I can do the same for frame. The frame 2 have all the cells that are in the frame 2. So we can get, for instance, the mean GFP at that time 2. The mean area if I take the mean of this column at time 2. For instance, we can also check this such as the GFP is less than 30. So you have here all like the cells which the GFP levels are less than 30, the same for like you can make this kind of logic um, test on the data frames, such as you can filter the data to the ones you want. Okay, so that's the idea. Here, this plots the area and GFP over time. And I check here the mean, as I told you. Here in the time, I select for all the times. Yeah, for instance, if I go df dot cell dot unique, I can get all the cells. If I have df time dot unique, I have I don't have time. I have frame. So these are all the frames that are in the data frame. So for all the, in this case it's time, but yeah, but this corresponds to all df, that is this guy. That is a new data frame. Okay, for that one, I take the mean area, the mean GFP, and the mean RFP. I plot them. You can check this more carefully. And I plot something like this. You can like play with this script. Maybe you have more questions I can help you to solve. Yeah, but everything is there. So let me fix the problem with the, or let me see the problem with the same, with the masks of Elastic, and maybe I can send you a small like message through mail. What's happening there? So you have any questions so far?
That was really good. Thank you so much. I think both Sophie and I will like try this for ourselves and kind of understand more intricately what you've been doing. But I think after that, we'll let you know if we have any questions.
Okay.
Yeah.
No, that's great. Maybe we can like try to confirm if like next week maybe can be also Thursday. We can like discuss a little more or have some questions.
Yeah. I think
That
we
works.
definitely, that would sound good. We have to download